This is AEC Example 8 from the structural section. And what they want you to do is find the internal forces at point X, which is 8 foot from the left support. And this is a free body diagram because it has, you have your reactions. I'm assuming these are reactions which are from support. So it'll probably be a simply supported beam, and this would be a roller. This would be, this could be a roller, and this could be a pin. But we'll just assume that this was a roller, this was a pin. There aren't any X forces in the X direction. There are no horizontal forces, so this is going to be 0. And that's how he got to where we're at. So anyways, there we are, and they want us to find the internal forces at X. And what you need to do is you need to cut the beam, and you take at X. So you want to cut the beam at X. So what we're going to do is we will cut the beam at X. You have 3,333 pounds. And this is a way you can find the internal forces anywhere on the entire beam, is by cutting it. You can cut it like a foot, you can cut it half an inch, and it will end up getting shear and moment diagrams. And that's kind of how you get your shear and moment diagrams as well. I'll show you that in time, that cutting the beam at here is the same as if you get a shear and moment diagram and looking at it as there. Once again, that's assuming you have knowledge of shear and moment diagrams, but we'll get there in time if you don't. But anyways, to find the internal moment, or the shear at this point on the beam and the moment at this point on the beam, we need to cut it there. So you have 5 foot. Wow, I'm really off base here. So what we're going to do is go 3 foot. And then I'll do this. And at every time you cut a beam, and we did an 8 foot, every time you cut a beam, it's kind of like a fixed connection. You're going to have a vertical force, a horizontal force, and a moment at that point. Of course, we know, since there aren't any actually you typically call this Vx, Vy maybe, yeah, let's call it Vy, why not? And then moment at point, let's call it moment at X, let's not call this. And then let's call it P, Px. Usually P, you'll use P for compression and tension loads. So we'll call this Vx because usually you say V is shear, and P at point, V at point X, and then P at point X, and then you also have moment at point X. So now all you do is you do the same thing. You use the equilibrium equations, which once again are some moments about a point equals 0, sum of the forces in the X direction equals 0, and then the sum of the forces in the Y direction equals 0. Once again, you have to isolate you want to isolate one of your unknowns. P, right now, you can already say that should be intuitive, but you should say the sum of the forces in the X direction equals 0. You don't have anything except Px, so whoops, P. So Px equals 0. Alright, so that's good. You have Px equals 0. You have nothing, no force in that direction. You're only going to only have shear and moment at that point. Now, we want to either look at this, use this equation or this equation. And looking at it, you can say, oh, well, let's not mess with the moments. That's a little bit more difficult since you have to multiply. Let's just add. Let's go say the sum of the moments. Some of the forces, I'm all over the place today. Sum of forces in the Y direction, there we go, equals 0. And you have positive 3,333 pounds minus 500 since it's going down. And then you have plus Vx. And I'm not even going to go through the algebra on that, but it's pretty simple. You take negative 5,000 plus 3,333 is 1,166, but that's minus 1,166 plus Vx equals 0. So you'll take the negative 1,667 and you put it on the opposite side. So Vx will equal a positive 1,667 pounds. And if you don't understand that, please work the algebra. It's pretty darn simple, and I'm not going to go over it, but we can do that in our head, and it should be obvious. If you have 5,000 down, you have 3,333 and 1,667 going up. That makes sense. All right. So this is the shear at that point. So at this point, the shear is going to equal 1,667 pounds. There you go. And to get the stress, you will also need to know what that beam is, but we're not at that point right now. We're not doing that, so we just say, okay, the shear is that. The shear force, I would say. Now, our last unknown is mx. Sum of the moments at point x equals 0. We're going to say positive is this way. Again, we just kind of guessed at this. I could have put it the other way, but I put it that way just because that's what I do. Usually I make them smile. And when I say smile, I mean I make the beam smile. If you are going to take that beam and you are going to put this moment on it right here, it's going to make the beam, I hope this is intuitive, go like this. So if you're pushing like that, it's going to make the beam deflect that way, and therefore the beam smiles. There's eyes. There you go, smiley face. All right, so the sum of the moments about point x equals 0. We are at point x, which is right here. I don't remember if you remember where we're at. That's point x. So v of x times 0 is 0. You will have m of x, moment at point x. P of x is times 0 is 0. You have 5,000. It's going to be a positive 5,000 because that's going to induce a moment in this direction, which is positive. So 5,000 pounds times it's 3 feet from our point, and then we want to do a negative 3,333 pounds times 8 foot. And once again, we know this is I made it a negative or a minus because this is going to make an opposite of our positive moment. We said positive moment is this. Oh shoot. Oh man. Okay, let's go back. I made a snafu here. What we could do is just, for this equation, I actually wrote it that this is positive, like so. Because I said, okay, we have a positive mx. Well, I said mx is going that way. We have a 5,000 pounds times 3, and that's going to create like that. So we just changed the convention here. It's now positive is we're going to say is going this way. All right. Positive is that way now. And a negative is that way. So we're good to go. Now let's go ahead and do the math and simplify. I will do the mx plus, well, that's going to be 1,500 foot-pounds. And this is going to be, what, my math in my head on that is not the best, so it's going to be 26,664 foot-pounds. And then we simplify here. Negative 26, 1,500. You're going to get plus a negative 11,664 foot-pounds. Then you flip this over here, and you'll get mx equals a positive 11,664 foot-pounds. And let's go ahead and check this from the book here. So hold on, I gotta flip pages. And when I look at the answers, we have V equals, I call it Vx equals 1,667 pounds, which is what we have. and the moment at x equals 11,664 foot-pounds. We are dead on. That is what they wanted us to find, and since we have a few minutes left, I could quickly show how we could do it the opposite way. You could solve on the other side as well. So it's not mutually exclusive saying, oh, you have to go left, right, or anything like that. And I'm going to go a little bit quicker this time. And later on, you'll learn that the shear moment diagram will get you the same thing. And then there's also these equations that they have them pre-made. Like, I know you've heard of WL squared over 8, and that's the equation to find out quickly find out a simple beam. You have a simple beam, and it's distributed with a line load on top of it, and that will give you the max. That will give you the moment at the center of that beam, which is the maximum. So, anyways, so they have those equations. They also have shear moment diagrams, or you can just cut it. So that's the 3 ways you can do it. We're going to cut it from the opposite side real quick. So let's draw it in there.
Daddy.
Hi, Liam. Where's Mommy? Oh, okay. That's Liam. You want to say hello?
Yeah.
Say hi.
Hi.
There you go. All right, so you have 1,667 right here. You're going to have 7 foot.
Daddy.
And then,
Daddy.
oh, I guess that's it. You don't have anything else. So, and then we're going to, well, you know this is going to be down. And then, since this is going this way, you know that this moment is going to be that way. So you now have m of x, and then this is going to be v of x. Notice we don't have any loads on this side, but we already know that. So if you say sum of the forces in the y direction equals 0, well, that's that. V of x is going to be 1,667 pounds. Because, okay, we had that, and then minus v of x. So you say v of x equals 1,667 pounds. Of course, that's in this direction there, and then on the opposite, you're going to have, I don't know if I've ever described the equal and opposite reaction. So if you have, if on this side of it, Vx is going to be down. On this side of it, on this side, when we did on from the left side, Vx is going to be up. It's just equal and opposite when you cut it. And if the moment's this way, on this moment, it'll be that way. Alright, so anyways, we're going to do sum of the moments. Sum of the moments about x, and we're going to call this positive. I'm going to equal to 0. And you say, okay, well, that's a heck of a lot easier going this way. Yes, sir? Oh, you want your shoes on? Okay. It's a heck of a lot easier this way when you just say, oh, 7 foot times 1,600. Okay, but this is a negative, remember, because it's going to create a moment that way, and we said that way is positive. So that's going to be a negative 1,667 pounds, which you could just say it's negative, and then it's going to times 7 foot, and this should equal what we just came up with, which is what? Which is 11,664, but let's just double check it. 1,667 times 7 equals 11,669. And I'm sure that's just slightly off because of us rounding or whatnot, which is no big deal. But there it is, 11,669. So that was a little bit easier than the way we got it over here because we didn't have 2 things to deal with. We just had 1 thing to deal with. So that in the future, when you're cutting, you can decide which way is easiest to decide which way you cut. And it's typically the side that you have, as long as you know all of your reactions, it's going to be a side that has less loading on it. So there we go, and that is it.